So to talk about ionic bonds, okay, ionic and covalent bonding, starting off the unit, we first have to talk about what is bonding. Because we're not talking about when you spend some time with a friend and you're like, oh, we're having such a bonding moment. No. A bond is a force that holds atoms together. Okay? So if we have two atoms, okay, there's an invisible force that bonds them together. Now, strong bonds are going to make it hard for this to break, and weak bonds are going to make it easier to break. Now, atoms bond because they want to achieve a stable electron configuration with 8 valence electrons. To take it back to you, remember if we're looking at the periodic table, and this is my little drawing here, and we've got our different rows, right? Oh, the P block is much shorter than it should be. We know that anything here has 1 valence electron, 2 valence electrons, 3, 4, and it goes all the way to 8. Okay, our noble gases here have 8 valence electrons. Okay, and column 1 has just 1. Now, when you have 8 valence electrons, for example, if you have neon, your electron dot structure looks like this. You have 8 valence electrons. Now, this is called the octet rule. Okay, when you have 8 valence electrons, you're stable. Okay, electrons like to be stable. Well, atoms like to be stable with 8 valence electrons. Now, when that happens, we know that a lot of atoms will do several things. We can either have magnesium, which has 2 valence electrons. It's much easier for those valence electrons to disappear and for it to have a +2 charge, right? It has lost 2 electrons. I'm positive I lost 2 electrons. Whereas fluorine naturally has 7 valence electrons. When you have 7, it's very easy to just add an 8th electron to become a -1 charge, okay? So bonds and atoms can achieve things different way. You can either do this by forming a ion, but it can also do multiple things, and we'll look into that later on. But I wanted to remind you of this um, electron dot and how we get our ions, right? Remember that anything that is charged is called an ion. Okay, that way, because that's what we've done um, in our past unit. Okay, now if we go back to the fact that there are two main types of bonds, okay, we know that ionic bonds form when one atom transfers their electrons, their valence electrons specifically, to another atom. And it's usually between a metal and a nonmetal. Okay. Now, if we are going to use an example, which let's go ahead and get rid of this over here, give us some room to work with, okay? If we're going to have a bond, for example, if we have sodium and chlorine, okay? Now, we know that sodium has 1 valence electron, but what's going to happen is it's going to lose that valence electron to become a +1 charge, and chlorine has 7 valence electrons, right? We know it wants to become an 8th to have a -1. But where, oh where, does that 8th electron come from? Where did it go? Well, what happens is sodium and its 1 electron and chlorine with its 7 electrons says, hey, I will give you my electron. It completely transfers so that now sodium has only 1 and chlorine has the 8 that it wanted with. So it's a complete transfer. And this is a very strong bond, okay? This is extremely strong because now the positive and negative attraction is keeping sodium and chlorine together. Now, we know that this transfer of electrons resulted in one positively charged ion, right, my sodium, and one negatively charged ion, which was our chlorine. Now remember that a positive ion is called a cation because cats have paws and cations are positive. And our anion is our negatively charged ion. Okay, now we know that opposite charges attract each other, similar to the north and south poles of a magnet. Positive and negatives attract each other. Okay, now, so ionic compounds have different properties. Okay, but an ionic compound is when you have two different elements, so sodium and chlorine, that come together to form one entity. Okay, now, all ionic compounds are also called salts. So NaCl is table salt, right? But MgCl2 is also a salt. It's called Epsom salt. It's what you put in your bath um, to release soreness in your muscles. Okay, but even if you have something with iron in it, okay, Fe2O3. That is also considered a salt because it is an ionic compound. Now, a single entity of this, if you have just one atom of Na and one atom of Cl that's been combined, we would call that a formula unit. Okay. Now, ionic compounds exist as solids at room temperature, and they easily dissolve in water. Okay, now that's not to say that covalent compounds cannot dissolve in water. It's just really easy for covalent compounds to dissolve in water because what happens is the water breaks up and gets in between the charged bond. Now, they also exhibit a crystalline structure. Crystalline structure. And this just means is that they're very ordered. So you'll often see things very cubic at the molecular level, where each corner of this is a sodium or a salt atom. They're just very structured this way. Now, they have very high melting and boiling points, and this is because they have strong bonds. Okay, in order for sodium chlorine or salt to melt, you have to break these bonds, and because they're so strong, it requires more heat. Okay, so you're gonna have to turn up the heat a little bit for those. And they also can conduct electricity in solutions. I kind of made a mistake here on the worksheet. You don't need a blank there, but they do conduct electricity. Okay. Now, the fact that they can conduct electricity makes them what we call an electrolyte. Okay. Now, electrolyte is anything that can dissolve, that dissolves in water and can conduct electricity. But that's a key word that you should know there. And ionic compounds also have high electronegativity differences. Okay. Now, as a refresher, electronegativity refers to an element's, I guess, willingness to attract an electron. Like, essentially, like, does it want an electron? Okay. Something like fluorine, which has 7 valence electrons, okay, really wants an 8th electron, so it has a high electronegativity value. But something like sodium, which only has 1 valence electron, has a really low electronegativity because it doesn't want another electron. In fact, it would much rather get rid of the 1 electron that it does have. So to list some common ionic compounds for us, we know that NaCl is table salt. That's an important one. We know that MgCl2 is Epsom salt. That's the common name used for soreness, things like that. So table salt is on your French fries. Epsom salt goes in your bathtub. Those are 2 ones there. Potassium bromide is used for your pets. to help cure like seizures and things like that with dogs. Okay, so just as a review, guys, we know that the main important thing that you need to know is that ionic bonds are transferred. Those electrons are transferred. So these valence electrons are transferred in an ionic compound. Okay, and that they have extremely strong bonds. Okay. Excuse me. So we have extremely strong bonds there. Let's get into covalent compounds. Now, ionic compounds are when electrons are transferred, but covalent bonds are formed when two atoms share, writing this wrong, or when two atoms share those valence electrons. Okay, and it's usually between two non-metal elements. Okay, um, so this means anything, if you're looking at your staircase on your periodic table, anything to the left is a metal, anything to the right is a nonmetal. So as long as you have only nonmetals, then it's going to be covalent. Okay, now because the electrons are shared, there are no charges. So if you have something like Na plus, that cannot be part of a covalent compound. First of all, because sodium is a metal, and second of all, because there's a charge. Covalent compounds do not have charges. Okay. Now, some common covalent compounds, one of the most common, H2O, water. Okay. Water is a covalent compound. Carbon dioxide. Carbon and oxygen are both on the right side, both nonmetals. Okay, it's what you breathe, all of that sort of thing. N2O, most commonly known as NOS, or what you put in your engine to make it go fast. So if you've ever watched the Fast and Furious movie, you have heard of NOS. There are lots of other ones, but those are two that immediately come to mind. So let's look at the properties of a covalent compound. Now, a covalent compound is also known as a molecule. Okay, so ionic compounds are formula units, covalent compounds are molecules, and they have very low melting and boiling points. This is because their bonds are weaker than ionic. Okay, it doesn't take as much energy to go through a covalent compound. They're flammable usually, and they do not conduct electricity in water. So if you were to have a beaker, okay, that's got some water in it, okay, and you were to take some sugar and dissolve it in there, okay, and then you had another beaker, okay, that also had water in it, and you were to dissolve salt in it, right? We both know that sugar and salt both dissolve. They're both white, but sugar is covalent, so this will not conduct electricity. And salt, which is NaCl, will conduct. Okay. Now, to show you how I know sugar is covalent, sugar is C6H12O6, right? All three of those elements are non-metal compounds, and you'll be able to determine that they are covalent. Now, back to our properties. So, they do not dissolve in water easily. Now, I know we just use sugar as our example for our covalent compound, and we know that sugar does dissolve pretty easily, but other things like carbon dioxide, NOS, a majority of covalent compounds are not going to conduct easily. Okay, and they are going to have low electronegativity differences. They're all kind of close to each other on the periodic table, so the difference between those two values are going to be very low. Okay, now some elements on the periodic table are what we call diatomic elements, and that means and they're all nonmetal. So some nonmetal elements on the periodic table exist only as pairs, okay, which are bonded covalently, and this is why they're under our covalent bond section. Now, what that means is if you were to have hydrogen gas, okay, hydrogen gas is never referring to just H. It's referring to H2, where you have a hydrogen atom bonded together with another hydrogen atom. You'll never see it by itself. Okay, it's either bonded to some other element or it's bonded to itself. And there are 7 of them: hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. Now I remember this as Hofbrinkel, and if you just remember that word, you can pronounce them out. Hof, H-O-F, Brinkel, B-R-I-N-C-L, Hofbrinkel. Okay, um, that may or may not help you. I hope it does, but that is something that you need to memorize, is these 7 um, things right here, 7 diatomic elements. So one thing is also make sure that you memorize that electrons are shared in covalent compounds, okay, whereas they are transferred in ionic. Okay. Now with the ionic and covalent, we talked about electronegativity, and I want to go back to that a little bit, but bonding is rarely purely ionic or covalent, in the same way that you would not have people who are purely evil or purely good, right? We don't have angels and we're not all devils, okay? We're a little bit in between. There's a spectrum, okay? We can determine whether or not something is going to be more covalent or more ionic by calculating the difference in their electronegativities. Now, we know that ionic has a high electronegativity difference and covalent is kind of low, but on our little chart here, this is should be 1 point. Okay. If your electronegativity difference, which is this triangle, and remember, difference is just a subtraction, okay? If the difference is greater than or equal to 1.7, you're going to be ionic, okay? And if your electronegativity difference is between 0.4 or equal to 0.4 and less than 1.7, you're going to be polar covalent. And all that means is that you are covalent, but you do have a partial ionic character, meaning that electrons are not shared equally. Okay, so in a normal covalent compound, or also considered non-polar, those electrons are shared equally. So if we were to draw this, okay, if we've got hydrogen and hydrogen, that's a non-polar covalent. These electrons are kind of equally spaced in between them. But if I were to have something that's maybe a little more polar covalent, for example, carbon and chlorine, okay? Chlorine is very highly electronegative, and carbon is, but not nearly as much as chlorine, and so the electrons are going to spend, see how, middle is right here? They're going to spend a little more time closer to chlorine than carbon. It's kind of like when your sister says, oh sure, I'll share my toys with you, but she gets it for 8 minutes and you only get it for 2, and your mom said y'all were supposed to share for 10 minutes, right? So it's not really sharing equally there. So we can also rewrite this chart. If this little chart is confusing for you, you can also break it down this way. If it's 1.7 or greater, it's going to be ionic. And if it's 0.4 or less than 1.7, it's going to be polar covalent. And if it's less than 0.4, it's going to be non-polar covalent. So really, you just need to know that. But you do have to memorize that. So let's look at some examples by filling in this chart. If we have bonding between hydrogen and hydrogen, okay, we know it's the same element, so the most electronegative one has to be hydrogen. There's no other comparison there. So to do the difference, you're going to take the most electronegative one, hydrogen, and subtract hydrogen, okay? Which all that means is you're going to have 2.1 minus 2.1. And when you do that, you're going to be equal to 0. Now, if I look at 0 on my chart, 0 is definitely less than 0.4. So that means you're going to be non-polar covalent. Okay. Now, if you have an atom that's bonded with the exact same thing, you're always going to be nonpolar covalent. There's never going to be a difference between the electronegativities there. But if we look at the second one, hydrogen and sulfur, we know that sulfur is going to be my more electronegative atom. It's got a value of 2.5, whereas hydrogen is just 2.1. So if we do our electronegativity, 2.5 minus 2.1 is going to give me 0.4. Now 0.4 is exactly on the line here, right? Exactly on the line. And 0.4 is going to be polar covalent there. You always go for the one above it, okay? So 0.4 will be polar covalent. Now, if we look at Na and Cl, now one thing, we know that this is going to be ionic because we know that Na is a metal and Cl is a nonmetal. So when we have that combination, it's automatically ionic. But chlorine, just to support our assumptions, chlorine is our most electronegative, and it's 3.0 minus 1.0. That gives us a value of 2.0. Now, if I look at 2.0, 2.0 is clearly above 1.7, so it will be ionic. Okay, now you can complete the rest on your own, but this set of notes will really help you for your test and just in the future with understanding our ionic and covalent compounds.